Okay, let's move to the third topic, which is the derivative of sinusoidal and the phasor. Let's see if we have the sinusoidal Vt is equal Va times cosine omega t plus theta. Right? The derivative of Vt is equal. Use the derivative of d cosine x dx is equal negative sine x, right? And so therefore we have negative. So we have a negative Va times omega times the sine omega t plus theta. So if we change that to cosine, so this cosine function using the trig identity we used before, that would be equal negative Va times omega times cosine omega t plus theta minus 90 degrees. If we move this sign into the inside the cosine function, we need to add, so that will be equal Va times omega times the cosine omega t plus theta minus 90 degrees plus 180 degrees, right? So therefore, we have Va times omega times cosine omega t plus theta, so that we have plus 90 degrees. So therefore, this is the derivative, and the phasor of the dvt dt is, we take the magnitude, right? We take the magnitude Va times the omega, and we take the phase angle, which is E2j theta plus 90 degrees. And if we rewrite this form, and we have Va times omega times E2j theta times E2j 90 degrees, and this one is equal j based on Euler identity. So therefore, we can rewrite this as j omega times Va times E2j theta. So this one is the phasor of Vt, right? So the derivative property is really very simple, and so the phasor of the derivative of the sinusoidal signal of a sinusoidal signal is the phasor of the sinusoidal itself with the original sinusoidal, okay? Original sinusoidal and multiplied by j omega. That's it. So this is probably the most important property. Also, that's the trick why we can avoid the differential equation. We will see this later as we do the circuit element constraint and the other things later into this course. And then I will go to the last topic of the phasor calculations. So we have the addition, subtraction, and in this case, the rectangular. If you calculate by hand, if you calculate using the computer program, the Python, as I did in the notes, in the Jupyter, in the Google Colab notes, and you can see it doesn't really matter using the rectangular form or the polar form. But if you calculate by hand, And the subtraction addition would be much easier if you have the rectangular form. Let's see, I have v1 is equal, let's see, v1r, so the real part plus j v1i, the imaginary part, right? And v2 is equal, let's say, v2r plus j v2i. And then if these two phasors add up, and that would be v1 plus v2 is going to be equal to the real parts add to the real parts, v1r plus v2r. And the imaginary parts just add together, so that's v1i plus v2i. Okay, and for the multiplication and the division, if you have polar, let's see, I have v1 is equal, let me just use a v here, v is equal va, and the phase angle is, let me use the exponential notation, e2j theta v. And if you have a current, and that's equal IA times e2j theta I, and then the product, if you multiply v times I, that's just equal VA times IA, the product of the magnitudes, and then you the phase angle, you just add them up, because the product of the two exponential functions, they add the exponents, and with theta I. And if for the division, v over I, right? By the way, v over I, that's the impedance we're gonna talk about later. And so this one is, this one would be equal VA over IA and times the E2J theta V minus theta I, right? So that's the for the multiplication and division in polar form. In the Google Colab notes, I also have what if you have the polar form and do the addition subtraction, right? And also if you have a rectangular form, you do the multiplication and division, and you can also check that notes. Okay, I'm not gonna go to the details. And so this will end the lecture number 1. And I'll see you next time. Bye bye.